Hi, this is Miss Gray. Welcome to Unit 12, Kinetics. This is, of course, AP Chemistry, so get ready for a wild ride. We're talking about rates of chemical reactions. So this is the podcast 12.1, and we're just going to investigate what do we mean by rates of reaction. First of all, there's a picture of 4 different reactions here, and I'd like you to arrange these reactions in order from fastest to slowest. The first one shows the picture of a gravestone that's being eroded over time into bits of sand and dust, gravestone erosion. The second one is an explosion, and it looks like a ship is exploding or something. In the third reaction, it's the rusting of iron, and in the fourth process, it shows dissolving, like dissolving salt or something. So which one do you think is the fastest? Go ahead and put them in order. Then in class, we'll talk about what it means to be a fast reaction or a slow reaction. By rates of reaction, we are simply talking about the type of change that occurs within an interval of time. So that's what rate really means, is measuring the change in a given amount of time. In chemistry specifically, we're looking at the concentration or the amount of substances that change per unit time. So change in concentration per unit time we would express in units of moles per liter per second, right? Moles per liter is concentration, and our units for time is seconds. For the reaction that's shown below, let's talk about how the amounts of substances would change over time. So this is the formation of ammonia from the elements nitrogen and hydrogen. So if we look at the concentration of hydrogen, for instance, then what we see, hold on, let me clear the writing. So what we would see for the concentration of hydrogen is that it gets used up during the course of the reaction, so the concentration of hydrogen decreases over time. What do you suppose happens to the concentration of nitrogen? Since it's a reactant, it's being used up, but it's not being used up as quickly as the hydrogen. In fact, we can say exactly how they compare. Because of stoichiometry, the concentration of nitrogen goes down 1/3 as fast as the concentration of hydrogen. And in a similar way, we can predict how the concentration of ammonia will change. The ammonia is going to increase at a rate that is twice as fast as the decrease in the amount of nitrogen. So as the reaction progresses, we started with 0 ammonia, and we're going to be producing ammonia over time. Notice how it levels out, right? Because once our reaction gets to equilibrium, the concentrations no longer change over time. So the reaction rate is describing the speed of a chemical reaction, and it's measured by the change in the concentration of reactants or products per unit time, with the units of molarity per second. Sometimes you'll see it written with m over s, big M over s, and sometimes you'll see it written with m times s to the -1 power. That's the same thing. They just use that s to the -1 power so that it takes up only 1 line of text instead of 2 lines of text. I guess book publishers like to save space that way. So the average rate, just like in physics, average rate describes the average change over time. So here it's the change in the concentration of a substance over time on average, but instantaneous rate is not the same. It could be the rate at any particular moment in the reaction, and of course most reactions are going to be faster in the beginning and then slow down as you approach equilibrium. So the average rate we would take like the total amount of change over the total amount of time. That's kind of like doing the slope. In fact, it's exactly doing the slope. So the average rate is change in y over change in x. But if we were looking at the instantaneous rate, then we mean like, what's the slope right here at this instance in time? And to figure that out, you find the slope of the tangent line to your concentration curve. This is a lot easier to do when you're using calculus, but let me show you some tricks for using algebra. So here's the decomposition of dinitrogen pentoxide to give nitrogen dioxide and oxygen. And we can collect measurements of each concentration as time progresses. So for 700 seconds, we have the data to show the molar concentration of the reactants, which are decreasing over time, and the products, which of course increase from 0 to their equilibrium concentration. Here's a graph to show what those concentrations are. So the average rate of change, we would take the beginning amount minus the final amount, so final minus initial, and then we divide by the total time. Did I spell it? No, I didn't spell initial right. Oh well, not a spelling test. Final minus initial divided by the total time, and that gives us the average rate of change. But as you can see, in the beginning of the reaction, the products are forming faster than they are at the end. So the rate doesn't remain constant. It's not a straight line. We're going to talk about how to get straight lines so we can calculate slopes easily. But in this reaction, it was not a straight line. So we're going to use that data and compare the amounts. Let me clear the writing here. So first of all, if we consider only the time from 300 seconds to 400 seconds, then we would find, of course, the concentration is final minus initial. So for the rate of oxygen change, we take the oxygen concentration at 400 seconds minus 300 seconds. So I got 0.0009 molar divided by the time, which is 100 seconds to go from 300 to 400 seconds. And that gives us a rate of 9 times 10 to the minus 6 moles per molar, what is that? Molarity per second? Moles per liter per second. There you go. How does this compare to the rate of change for, say, NO2? Let's calculate it. Take the change in concentration divided by the change in time. And what I find is that the rate of change for NO2 is greater than the rate of change for oxygen. We could have predicted that by stoichiometry. Let's look at that chemical reaction again. Here it is. For every 1 oxygen that is formed, we get 4 nitrogen dioxides forming. So the rate should be 4 times that of the oxygen. And it's pretty close, because 9 times 4 is 36, and we got 37. So why is it not exact? Well, because it's not an average, it's just the one shot. And then for dinitrogen pentoxide, we would do the same process. We get 1.9 times 10 to the minus 5, because for every 1 oxygen that is produced, 2 dinitrogen pentoxides are consumed. So that rate of disappearance of dinitrogen pentoxide is twice the amount of the rate of formation for oxygen. So for any reaction, let's call this the reaction of A plus B to form C plus D, so just some generic reaction, the rate is going to be equal to your coefficient in a fraction times the rate of change in that substance divided by the time. So take those coefficients and put them into your rate so you can compare one to the other. And notice the sign here too. I have a negative rate for substance A and substance B because those are reactants and they are being used up. These substances are disappearing. Their concentrations are going down. And I probably spelled that wrong too. And then the products are forming. These are being produced, so their concentrations are increasing, and so those fractions are positive, not negative. And that's how we work with rates. So next time I'll show you how to use experimental data to calculate a rate law.